This study presents a comprehensive theoretical investigation of the ionization potentials of the alkaline earth metal fluoride molecules, specifically CaF, SrF, and BaF. The research employs the state-of-the-art relativistic coupled cluster approach with single, double, and perturbative triple excitations, CCSD, utilizing the Dirac code to account for relativistic effects. The calculations were performed using various diol basis sets, including valence, core valence, and all electron variants, with additional diffuse functions added to improve the description of the bond region and valence properties. The potential energy curves of both the neutral molecules and their molecular ions were calculated using the CCSD approach, and the ionization potentials were obtained as the difference between the energies of MF and MF+ at their corresponding equilibrium bond lengths. The final results were obtained from a complete basis set limit, CBSL, extrapolation of the potential energy curves based on the SOG CVNX, n equals 2, 3, 4, basis sets, following the scheme of Helgaker et al., 45. Two other CBSL extrapolation approaches were also tested, namely the schemes of Martin, 46, and Lisiak and Yziorsky, 47, which confirmed the convergence of the calculated IP with respect to the basis set cardinality. The calculated spectroscopic constants of the ground states of the neutral molecules and molecular ions are presented in Table I, demonstrating good agreement with previous calculations and experimental values. The least numerically stable value is the anharmonicity correction omega e chi, although the experimental uncertainty for these constants is often high. The IP values obtained using different basis sets are presented in Table 2. These calculations were carried out correlating 25, 35, and 35 electrons, respectively, and setting the virtual space cutoff at 50 A.U. The adiabatic IPs, derived from the molecular energies at the equilibrium geometry, are also given in Table 2. These results are in excellent agreement with the measured values for CaF and barium fluoride, and provide a new accurate prediction for SrF, which deviates from the available experimental data, motivating further experimental investigations. This research paper presents a comprehensive study on the adiabatic ionization potentials, IPs, of alkaline earth metal monofluorides, specifically focusing on calcium, strontium, and barium fluorides. The calculations were performed using the CCSD method, which is a highly accurate computational approach that accounts for both electron correlation and core correlation. The results obtained from this method were further corrected for higher-order contributions, including electron correlation, core correlation, and quantum electrodynamics (QED) effects. The spectroscopic constants of the ground state for these molecules and their corresponding ions are provided in Table I. These results are based on the complete basis set, CBS, limit, with 25, 35, and 35 electrons correlated for calcium, strontium, and barium fluorides, respectively, and a virtual space cutoff of 50 A.U. The adiabatic IPs calculated using the CCSD method are listed in Table 2. With corrections applied for higher-order contributions such as the effect of augmentation functions, limited active space, residual triple excitations, and QED effects. The main sources of uncertainty in the calculated IPs are detailed in Table V, including the effects of basis set cardinality, augmentation, core correlation, virtual space, higher excitations, and relativity. These uncertainties are combined to provide a total uncertainty for each molecule, as shown in Table V. The final recommended adiabatic IPs, along with their corresponding uncertainties, are presented in Table V. Additionally, the vibrationally corrected adiabatic IPs are also provided, taking into account the vibrational frequencies of both the neutral and ionized molecules. Comparing the calculated IPs with available experimental data, the results for calcium fluoride exhibit excellent agreement, demonstrating the accuracy of the computational approach and the reliability of the uncertainty assignment scheme. However, the calculated IP for barium fluoride shows a larger discrepancy with the experimental value, which could be attributed to the higher sensitivity of this system to the quality of its description. The large error bar on the measured value for strontium fluoride, combined with the discrepancy in the calculated IP, suggests that an accurate measurement of this in heavier monofluoride molecules would be beneficial. Overall, this study provides highly accurate theoretical predictions of adiabatic IPs for calcium, strontium, and barium fluorides, along with detailed uncertainty estimates. These results can serve as a benchmark for future experimental studies and further theoretical investigations of these molecules. This research paper presents a comprehensive study on the ionization potentials, IPs, of calcium, strontium, and barium monofluorides using the four-component relativistic coupled cluster method with large uncontracted basis sets and extrapolation to the complete basis set, CBS, limit. The study also includes BREET, QED, and higher-order excitation corrections. The results show excellent agreement between calculated and experimental IPs for CaF and barium fluoride, with a new prediction for SrF. The work highlights the suitability of these molecules for laser cooling, which is crucial for precision measurements, such as the electric dipole moment of the electron. The paper discusses the importance of these molecules in various fields, including quantum computing, precision measurements, and chemical reactions. It also provides a detailed analysis of the effects of different computational parameters on the results, allowing for the assignment of realistic error bars on the predictions. The study employs a range of theoretical and experimental techniques, including relativistic Hamiltonians, QED potentials, and basis set convergence, to ensure high accuracy in the calculations. The paper concludes by discussing the implications of these findings for future studies on these molecules and their potential applications in different areas of research. It also acknowledges the support from various institutions and grants that made this work possible. Here is the combined summary of pages 7 and 8 of the research paper. Theoretical studies of molecular properties require accurate calculations of relativistic effects, particularly for heavy element systems. To this end, the authors employ the Tel Aviv relativistic atomic Fock space-coupled cluster code, TRAFS3C, to compute radiative corrections to energy levels and electromagnetic amplitudes in many electron atoms. This code has been previously applied to calculate nuclear antipole moment interactions, ionization potentials, and electron affinities in various systems. The authors also reference recent experimental studies on spectroscopy of short-lived radioactive molecules, highlighting the need for accurate theoretical calculations to support these experiments. In particular, they cite the measurement of isotope shifts in radium monofluoride molecules, which requires precise calculations of relativistic effects. To achieve this, the authors employ a coupled cluster method, which includes relativistic corrections up to second order in the fine structure constant alpha. The method is based on the relativistic many-body perturbation theory, incorporating polarisation effects and QED radiative corrections. The authors present the key equations governing their approach, including the relativistic coupled cluster amplitude equations and the expression for the energy correction. They also outline the computational procedure, involving the calculation of the 1 and 2 body matrix elements, and the iterative solution of the amplitude equations. The authors highlight the importance of including relativistic corrections in the calculation of molecular properties, particularly for heavy element systems. They also discuss the limitations of their approach, including the neglect of higher-order relativistic corrections and the assumptions made in the computational procedure. Future work directions include the extension of their method to larger molecular systems and the inclusion of additional relativistic corrections.